Our last section in this chapter, and indeed that we'll look at when it comes to matrices, ties all this stuff back together. We started off to chapter 4 looking at solving systems of linear equations. We took this detour in the last couple of sections into matrices and inverses of matrices. So now we're going to tie this back. Why have we been doing this? Right? So suppose I have the following. Suppose A is an n by n matrix, and X and B are n by 1 column matrices. We want to solve a matrix equation that looks like this. You can have all sorts of different matrix equations, but I want to solve this particular matrix equation, which means I want to solve and isolate X. I want to figure out what X is. How do I do that? Well, if these were just real numbers, you would say, well, all I need to do is divide both sides of the equation by A, right? That's all you'd have to do. But there is no division with matrices. There's no such thing as division. There's only matrix addition and multiplication, and scalar multiplication as well. So if I can't divide, how do I solve for X? Well, just as with real numbers, suppose this was like, suppose these are real numbers, AX equals B. Instead of thinking of division, you would think of, I need to multiply both sides by the inverse of A, right? You would say, I need to multiply both sides by the inverse of A, and then they would cancel out, and then I would have X isolated. That's what we're doing here. So because there's no division, I'm multiplying both sides by the inverse of A. So multiply both sides by the inverse of A. There's another catch, another very important catch is when you're working with real numbers and you say, okay, multiply by the inverse of A on both sides, you wouldn't really think about whether you're multiplying on the left or the right. What I mean by that is I just had AX equals B, and you might say, I'm going to multiply both sides by the inverse of A, and for real numbers this would be fine, but on the left here, on the left of the right of the equal sign, I've multiplied this equation on the left by 1 over A, and over here I multiplied on the right by 1 over A. That's fine with real numbers because multiplication is commutative, but remember matrix multiplication is not commutative in general. So I have to be very careful that I write this, if I'm multiplying on the left here by A inverse, I have to multiply over here on the left by A inverse. So it's A inverse B and not B times A inverse. It matters, right? So multiply by A inverse on the left. There's also something else. When I write A inverse here, I'm assuming that it actually exists. All right, so suppose A is n by n. It's also invertible. So suppose that A inverse actually exists so that I can do this. And why did I do this? Well, because matrix multiplication is associative, so let's just regroup this. This is A inverse times A times X, which is A inverse times B. And what is A inverse times A? A inverse times A is the n by n identity matrix. By definition of them being inverses, so that's In times X is A inverse times B. And what's the identity matrix times X? Well, identity matrix plays a role of multiplying by 1. It doesn't do anything. So In times X is just a long way of writing X. So this means X is A inverse times B. So for this particular matrix equation, assuming A is actually invertible, an inverse exists, then we can solve it and find that X, by multiplying both sides on the left by A inverse, X is A inverse times B. So the catch here is just remember, there is no division. There's no division with matrices. I can't divide, but I can multiply by the inverse. So let's work with some actual matrices here. I'm going to tell you what A is and what B is. Okay, so same thing, but now we have some actual matrices here. A is this 3 by 3 matrix, 1, 2, minus 1, minus 4, minus 7, 3, minus 2, minus 6, 5. X is our unknown matrix. It's this unknown column matrix, x1, x2, and x3. And B, I've given you a column matrix there, 1, 2, 0. So once again, we're asked to solve AX equals B for these particular matrices. And assuming A is invertible, assuming an inverse exists, we've just seen that X is going to then be A inverse times B. Okay, so x1, x2, x3 is going to be the inverse of A. And you would have to go and solve for the inverse of A. You'd have to find the inverse of A. But this is in fact the matrix we did at the very end of the last section. So we already found the inverse of A in that case. And we found that the inverse of A last section was, for this guy, was minus 17, minus 4, minus 1, 14, 3, 1, and 10, 2, 1. Okay, and we're going to multiply that by B, so 1, 2, 0. And now we just have to carry out this multiplication. This is all there is to it. So now I just have to multiply A inverse by B, and what do we get? So we've got minus 17 times 1 plus minus 4 times 2, so minus 17 plus minus 8, and then plus 0. Minus 17 plus minus 8 is minus 25. Next entry will be row 2 times column 1. So we've got 14 times 1 plus 3 times 2 plus 1 times 0. 14 plus 6 is 20. And last but not least, we've got this row by this column. 10 plus 1 is 10, plus 2 times 2 is plus 4 is 14, plus 0 is 14. So it turns out the solution to this matrix equation is x equals minus 25, 20, 14. Right? Or, so let's write this down. So x is this matrix. It's minus 25, 20, or 14, and 14. Or, but if I look at this individually, this tells me exactly what the entries are, right? It tells me the entry x1 is minus 25, x2 is 20, and x3 is 14. So there's the solution to this matrix equation. But where do linear systems tie into this? Well, it turns out that this matrix equation actually represents an underlying linear system that we just solved. So let me explain. Let me show you how this works. So what does AX equals B represent? Well, let's actually write this down. So we never actually wrote down what we're looking at. So let's write down AX equals B. We've got 1, 2, minus 1, minus 4, minus 7, 3, minus 2, minus 6, 5. Then we've got x, x1, x2, x3 equals b. 1, 2, 0. Okay, well, what if I carry out the multiplication over here on the left-hand side? Let's multiply these together. So, row 1 by column 1 is going to be 1 times x1, x1, plus 2 times x2, plus minus 1 times x3, so minus x3. And that's the only entry. How do I know this? Because it's 3 by 3 times a 3 by 1, so the output is going to be a 3 by 1 matrix, so 3 rows, 1 column, and it's just this row by this column. Next entry is going to be this row by this column. So I'm going to have minus 4 times x1, plus minus 7 times x2, plus 3 times x3. And last but not least, we've got minus 2 times x1, plus minus 6 times x2, plus 5 times x3. So there's the product of these two matrices together, and that still equals the right-hand side. 1, 2, 0. Okay? Well, how are two matrices equal to each other? The only way two matrices are equal is if they're the same size, which these are, and if their corresponding entries are equal, right? So this entry has to equal 1, this entry has to equal 2, this entry has to equal 0. So the only way these are equal is if x1 plus 2x2 minus x3 is equal to 1, minus 4x1 minus 7x2 plus 3x3 is equal to 2, and if minus 2x1 minus 6x2 plus 5x3 is equal to 0. Well, what is that? That's a system of linear equations, right? It's a system with 3 variables and 3 equations. So this matrix equation, AX equals B, this represents this linear system. And we just solved it, right? By finding the inverse of A, we were able to write down the solution X, which gives us solutions for X1, X2, and X3, gave us solutions for X, right? X was A inverse times B. And using nothing but matrix techniques and finding the inverse of A, we found, and we solved this system. We solved this and found, as we just did, we just found x1 was minus, I believe it was minus 25, x2 was 20, and x3 was 14. So this is sort of a really interesting and really powerful technique for solving linear systems, is representing them using a matrix equation. So you can, of course, backtrack and then convert this back to a matrix equation. Represent them as a matrix equation, and then just solve for x equals A inverse times B. It does have some downsides. It requires you to find the inverse of a matrix, which can be difficult because it takes a little while. But it does have the upside in that once you've found that inverse, so x is A inverse times B, x is A inverse times B, if you change B, meaning, if I change B, meaning I'm changing the values over there on the right-hand side, I don't have to go ahead and resolve and do Gauss-Jordan elimination on a brand new system with new values over here. If I change B, all I have to do is plug in different values for B. And I believe some of your homework problems will look like that. It will sort of specify different values for B for the same system, and all you have to do is find the inverse once, and then just plug in different matrices there for B, different values for B. So there's the upside. How do you go backwards? So yeah, so B is just everything to the right of the equal sign. And A is usually called the coefficient matrix, because you'll notice that the entries here are just the coefficients of the x values, or the x variables. All right, so A is what's called the coefficient matrix. It's everything that would be on the left-hand side of the augmentation bar when you're doing your augmented matrix. So you can always do this. Well, I shouldn't say always. You can do this in the cases where A is actually going to be an invertible matrix, meaning it has to, at the very least, have the same number of equations as variables, right? So it's got to have the same number of rows as columns, so that would result in a square matrix, an n by n matrix. But let's write down some of the details of this. So formalizing what I was just saying, clearing it up a little bit, so every system of linear equations can always be given by a matrix equation of this form, AX equals B. You can always convert it into a matrix equation. And it's going to have this solution, x equals A inverse times B, assuming A inverse exists. And assuming A inverse exists, that first and foremost requires it to be square, because only square matrices have inverses. And since A is giving the coefficients of the entire system, for that to be square, that would mean that your number of equations has to equal your number of variables. If it doesn't, if you're not in this situation, then you can't apply this technique, but that's okay. We have other techniques for solving systems. You can just use regular old Gauss-Jordan elimination from 4.3 to solve your system. As I said, using this technique has upsides and downsides. The upside is that you can change your B, you can change your stuff to the right-hand side of the equation and resolve the system very quickly. The downside is you have to find the inverse of A if it exists, and that it can take a little while. Remember, it's not so bad for 2x2s because we have this really nice formula for 2x2 matrices, but for 3x3 and bigger, it can take a little bit of work to solve for A, or to solve for A inverse, I should say. So all I want to do is one example, because they take a little while to find the inverse, but once again, if you want to see more, check the textbook, there's quite a few in there. Here's a typical example. We've got a 3x3 system, 3 equations, three unknowns, 3 variables, and we want to solve it. So here's the system: 3x1 minus x2 plus x3 equals 3, minus x1 plus x2 equals minus 3, and x1 plus x3 equals 2. So we're going to use matrix methods here. So we're going to solve ax equals b, where A is the coefficient matrix, so coefficients of x1, x2, and x3. We've got 3, minus 1, and 1. Coefficients of x2, minus 1, 1, and 0. And coefficients of x3 look like 1, 0, and 1. X is just our unknown column matrix, x1, x2, and x3. It's the variables. And B is everything to the right-hand side, 3, minus 3, 2. So our solution is going to be x is A inverse times B. If this was 2x2, we would just use our formula, very quickly write down the inverse of our 2x2 matrix A and solve for x, and we'd be done. But this one's a slightly longer example. We have to find the inverse of this 3x3 matrix. So we're going to look for A inverse, and we'll use the techniques we developed to find A inverses. So I put my matrix on one side of the augmentation bar, Since it's 3x3, on the other side I put the 3x3 identity matrix. Okay. Let's see. I'm going to need a lot of space. Well, I won't worry about the space just yet. We'll just carry out our first step. What do? Gauss-Jordan elimination. I want to put a 1 right here. I could divide this equation by 3, but that introduces fractions. Or not this equation, but this row. That introduces fractions. Let's put a 1 right here just by flipping row 1 and row 3. Row 1, we'll flip that with row 3. And we'll have 1, 0, 1, 0, 0, 1, minus 1, 1, 0, 0, 1, 0, and 3, minus 1, 1, 1, 0, 0. And before we go any further, let's just stop and check very, very quickly. Have we made any copying errors or anything like that? Everything looks okay. Okay. Why am I being so careful? Again, because I've done lots of these and I've made mistakes many, many, many times. Be very careful as you go through every step. Double check them, triple check them all before you move on to the next step. So I need lots of space, so I'm just going to erase all of this. And I think the only thing I really need to keep on the board to remind myself of is B. So there's B for later. But for now, we're just going to keep going with our row reduction. So we'll bring this over here. And what do we want to do? We want to add row 1 to row 2 to put a 0 here. And we want to subtract 3 times row 1 from row 3 to put a 0 right here. So row 2 plus row 1 will become our new row 1. And row 3 minus 3 times row 1 becomes our new row 3. And okay, so row 1 is going to stay the same. I'll just copy this down. And now we're adding row 1 to row 2, so we've got 0, 1 plus 0 is 1, 0 plus 1 is 1. Keep going past the augmentation bar, we've got 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1. So we're looking at 0, 1, 1. And now we're taking row 3 and subtracting 3 times row 1 from it, so 3 minus 3 is 0, just as we wanted. Minus 1 minus 3 times 0 is minus 1. 1 minus 3 times 1, 1 minus 3 is minus 2. Then we've got 1 minus 3 times 0 is 1, 0 minus 3 times 0 is 0, 0 minus 3 times 1 is minus 3. Quickly double check all of our calculations. Everything looks okay to me, so we'll move on. Now we cross off this row mentally, and we want to put a non-zero entry right here to use to zero out everything below it. A 1 would be ideal, which we have. So all I have to do is add row 2 to row 3. Row 3 plus row 2 is our new row 3. And we're looking at 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1. Now we're going to add row 2 to row 3, so 0, 0, minus 2 plus 1 is minus 1. 1 plus 0 is 1. We're just adding them, right? Yeah. 0 plus 1 is 1. Minus 3 plus 1 is minus 2. Okay. I wanted to keep B on the board, so I won't erase that. What now? Now I want to put a non-zero entry here. Well, there's a non-zero entry. I want to rescale it to be a 1, and then I want to use that to zero out everything above it. So let's rescale this to a 1 very quickly. How do I do that? I just multiply the entire row by minus 1. So minus row 3 will become our new row 3. One, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, and we're just multiplying this row by minus 1. So we end up with 0, 0, 1, minus 1, 2. Okay. We use that to zero out everything above it, so all I have to do is subtract this row from these two rows. So we'll have row 1 minus row 3 is our new row 1, and row 2 minus row 3 is our new row 2. Zero, 0, 1, minus 1, 2. And okay, we're subtracting row 3 from row 2. So 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 1 is 0. 0 minus minus 1 is positive 1, 1 minus minus 1 is positive 2, 1 minus 2 is minus 1. Really quickly check these calculations. Everything looks okay. And we're doing the same thing up here. Row 1 minus row 3. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. 0 minus minus 1 is positive 1. 0 minus minus 1 is positive 1. 1 minus 2 is minus 1. What now? Okay, now I come to this second leftmost one. I rescale it to be a 1. It is. I use that to zero out everything above it. It is. We're already here. I have I3 right there, meaning this matrix is A inverse. So we found the inverse of A. And now that I've found the inverse of A, I can write down the solutions to the system. So, solution, we've got X is A inverse times B. So X is going to be A inverse 1, 1, minus 1, 1, 2, minus 1, minus 1, minus 1, 2, times b. 3 minus 3, 2. Alright, so now we just have to carry out this simple matrix product. One row, first row by first column is going to be 1 times 3 is positive 3, plus 1 times minus 3 is 3 minus 3 is 0, plus minus 1 times 2 is just negative 2. Again, I'm just carrying these out mentally. Double check them if you want. But next up we've got 1 times 3 is 3, plus 2 times minus 3, so 3 minus 6 is minus 3. Plus minus 1 times 2, we've got minus 3 times minus 3 plus minus 2 is, we're at minus 5 there. And just check this again, 3 plus minus 6 plus minus 2. 3 plus minus 6 plus minus 2 is minus 5, yes. Then we've got minus 3 plus positive 3, so that's 0, plus 2 times 2 is 4. Well, there's x. And what was x? X was the matrix that looked like this. It was x1, x2, x3. So that means x1 is minus 2, x2 is minus 5, and x3 is 4. x1 is minus 2, x2 is minus 5, x3 is 4. And there's our solution to the system. Took a bit of work to find the inverse, but again, the better you get at this Gauss-Jordan elimination, the more you practice it, the more you do it, the faster you'll get. So finding an inverse of a 3 by 3 is not that bad. We haven't done any larger examples, no 4 by 4s, 5 by 5s or anything, but of course it gets more and more complex the bigger you get. But in this class we'll stick to 3 by 3s. Okay, so this is the method. If you have a coefficient matrix that's square, you can try to find the inverse, and if the inverse exists, then your solutions to the system are just given by A inverse times B, where B is everything to the right of the equal sign. Again, if you want to see more examples, there's more in the book, but we'll stop here. Thank you.